Thank you for inviting me to give this talk. I've been to Lund the first time in 1995. At the beginning of my PhD thesis, I was at the Department of Mathematical Physics to learn about mathematical modeling, physical modeling of thermal heat stores. And at that time, I also visited Karl Johann's department and worked together with Sven Erik, also met Hilding when he was having one of the first Ericsson mobile phones. It was a very inspiring time here in Lund. And soon after, I joined ABB in 1998. And since then, I've always been working with model-based control, which at the end means optimization. So to bring optimization to industrial applications. In this talk, I'd like, after a short introduction, short overview, to take a step back what we did with steam power plant optimization. Steam power plants, at least in Europe, are declining nowadays. So we had quite some work when hard coal-fired power plants went from a constant operation to more daily, day-by-day operation to optimize startups of those. But now they are used less and less, and many of them are now hardly start up anymore at all, at least during summer times. We did a lot of work in electrical system optimization. I was able to pick up work which has been done by Hans-Jörg Wiesmann before. Many of you will know him from the early times of the Modelica. And now we make very good use of this work for the optimization of electrical systems. The power production, while the big power plants are declining, more and more small power plants are coming up. So I'd like to give a short overview about virtual power plants. We are doing more and more nowadays. If time permits, I'd also like to say a report about some bad experiences with FMI and Modelica, or you may also shift it to the panel discussion later. So the way we do model-based applications is we standardized on two levels. We standardized on the model formulation level on using Modelica, and this helped us a lot. While the power industries was completely changing during the last decade, we could keep on using the same tools. We used Modelica for water steam models, for boiler models. Before, we are still using this, mostly in Asia. We have many projects still running. But we do also use Modelica for smart cities and virtual power plants, where the focus is much more on the electrical side and on the aggregation of lots of small producers. And we can even use it like here we did work on the optimization of wake effects in a wind farm. There we could even use Modelica. No matter which physical domain we model, we translate the model to a functional model interface. I call it not mock-up interface because we use it in the real system for the control of the system. And the good thing is, like for thermofluid, Daimler has always been the best tool. It is still the best tool due to its really blazing fast user interface. For other systems, we use the Modelica tool by ISI simulation, and we increasingly are using OpenModelica. No matter which tool we use, we can load the same Modelica libraries, and we can generate the same FMU. And those FMUs we are deploying on different platforms. We don't go down extremely small. So we say the least requirement we have is an x86 64-bit processor. Those boards start at like 100 euros. Such an IPC here costs like 400 euro. We don't go smaller because we don't want to take the pain, all the disruptive changes in the software development chain you would have to do there. We still want to be able to load a dynamic link library to pass an XML file on those devices. But we scale up. So the most applications we did on server PCs, redundant servers installed in some computing room on-site the plants, so-called on-premise installations. Nowadays, we have increasing cloud installations where like for a virtual power plant, you don't have a physical site where the plant is situated. It's natural that you place the servers in some computing center, which is not real cloud, it's more hybrid cloud or private cloud. But we do also have more and more real cloud installations where customers are fine with having the computations running somewhere. They don't care. And all of us, we can save a lot of effort by not having to design such rooms and build the PCs by just clicking a button, as Costa said, giving in the credit card and saying, I need this PC now. And next week I don't need it anymore, then I turn it off again. Based on the functional model interface, this functional model interface gives us a mathematical model. And the good thing is we use FMI for model exchange because this is really a mathematical model where we have continuous time states, discrete time states, we have model outputs, and this is the majority of what we need for the optimization problem. Outside the FMU, we add objective function, which oftentimes is like linear or quadratic weights on model variables on some dedicated model outputs, but the sophisticated equations are formulated inside the model. And we add constraints, which again mostly is lower and upper bounds, either hard constraints or soft constraints on model variables that we have in the FMU. And based on that model, this we solve, then I come back to this later, to newer developments. This we solve on the machines, which scale from small IPCs to big cloud installations and multi-core machines. Steam power plant optimization. This is a slide from a Eurosyslib meeting in the last decade. Here I took just a figure from a thermodynamics textbook, a process flow sheet of a steam power plant. And at that time, we formulated some requirements, what from this we would have to bring into Modelica. Like the operating conditions, they are oftentimes specified outside the components. They are not assigned to components, but they are assigned to the connections between the components. Steady state is very important. Modelica traditionally focuses on dynamic simulation, but in such systems, steady state is very important, the coverage of steady state models. Engineering units, yes, we can sound this on SI, but in power plants, no one wants to work with Pascal and Kelvin, and in the US, they don't want to use bar even, or degree centigrade, so we need to be flexible regarding the engineering units. We have strongly coupled fluid networks, and this causes a lot of headache for the numerical treatment. And last but not least, already at that time we saw there is always electrical side, even though at that time we still focus on the thermal side. This is from a presentation at the Modelica conference 2009 in Como. So the major introduction into Modelica was that we had problems with so-called calculate mixing enthalpies between connected components because those mass flow equations contain Boolean variables for the direction of the fluid flow. And also we formulate a mass flow balance and we formulate additionally an enthalpy flow balance. So this we changed to a stream-based calculation. We introduced stream variables which go on top of a flow. So if once we decouple the calculation of the enthalpies from the calculation of the mass flow rates, and then once we have determined the mass flow rates, we pick the right enthalpies. That we introduce stream variables and this in-stream operator, that each component knows what enthalpy is outside that would enter me if flow would go into me. This is one I changed during the lunch break after our discussion and also after Karl Johann's talk this morning, because there's so much discussion about model reduction. So what we did in the fluid, each model has a system model, and in the system model we have a tab assumptions. We make modeling assumptions for the whole system, but you can also dig into particular components and override the modeling assumption for the particular components. And there we can say for the mass dynamics, for the energy dynamics, and for the momentum dynamics, we can individually decide if we have dynamic with free initial values, with fixed initial values, if we have a steady state initial point, or if the whole equation over the whole time horizon should be a steady state model. And depending on those settings, the Modelica tool generates different mathematical formulations, which are then exported into the FMU. So, and this is what allows us, even though fluid, everyone might agree that it's a beast of a library, it's huge and complex, but with those assumptions, we can still use it and can reuse all the testing and all the effort that went in the library. So we use it, for instance, for soot blowing optimization. This is when in a boiler, you have lots of measurement on the water steam side, but you have only very rare measurements on the flue gas side. You have heat exchangers between the flue gas and the water steam side, and those need to be cleaned regularly. If you clean the heat exchanger, you lose energy because you need typically use steam for cleaning those, and the steam needs to be produced and is wasted afterwards. Meaning if you clean too much, you have a very clean boiler, but with a not perfect efficiency. If you clean too little, it's the opposite. You have so much soot in the boiler that you lose efficiency, which you better would invest into cleaning to improve the efficiency. And there is a typical optimum, how much cleaning should be applied. And then you see such a curve. This blue curve is the efficiency of the heat exchangers. In order to determine this efficiency, as we don't have measurements on the flue gas side, we use a system model. We use the over-determined measurements on the water steam side to calculate the measurements on the flue gas side, and from this calculate the efficiencies of the heat exchanger. And this is a fluid model which we adapt, which we even extended with non-SI units so that we can also use it in outside Europe or in US in particular. Another application, do I still? No, I don't see it here. But this was, at least it was published 2006, and this was one night in February in 2004. Was basically the first startup of a coal-fired power plant which we did with a nonlinear model predictive control. So at that time, we didn't have the fluid library, but we evolved the application towards using the fluid library in newer installation. At that time, we made a model where, the equations at the end are similar, but not as nicely structured as we can do it now with the Modelica fluid library. What you see here in this figure, you see the startup process of a coal-fired power plant. Here you see the fuel flow rate. You see how the pressure at the end of the boilers builds up, how the live steam flow builds up. And you see thermal stress in components. If you heat up a power plant by several hundred degrees centigrade, you have stress in thick-walled, geometrically constrained parts of the power plant. And this stress limits the maximum speed you can start up the power plant. But again, it's an optimization. There is some allowed stress for the expected maintenance cycle, and you should exploit this stress, not go below. So the NMPC has to control along the stress limit such that the power plant goes up as efficient as possible. And here you see an example where the light blue lines, they show the predictions which we do at each minute for the whole startup. The dark blue points are measurements from the plant. Initially, we wanted to go up to 12% with heavy oil startup fuel, but the burners didn't do this at the beginning. Later on, they were overshooting. So in this overshooting resulted in a violation of the predicted thermal stress. And then the NMPC immediately reacted by reducing the fuel flow, by throttling the valve at the outlets or reducing the steam flow, such that we can control it back to the limit, the thermal stress. And you see we have some more disturbances, so over almost 3/4 of an hour we controlled the plant along the allowed thermal stress by manipulating the fuel flow of startup fuel and the steam flow. And then here you see the coal mills who start, and then the regular operation starts in the power plant. So this is an example, a nonlinear model predictive control which we have installed in a couple of coal-fired power plants meanwhile. Whenever a power plant has to start up at least once a week, it makes a lot of sense to have such an advanced startup control. I'd like to come to electrical system optimization. It's actually the electrical applications are older than the thermal applications in ABB. This was work by Hans-Jörg Wiesmann in the RealSim project year 2000. He was applying, or he was modeling drivetrains, electric drivetrains of electric trains. And this work he continued on afterwards, and then it took until 2012, basically now maybe 2010, that we took this work over and put it to use. One of the first uses was modeling of wind turbines. I did already show before how we modeled wake effects in the wind farm. And here you have a model of the wind farm, and you can drill down. Each wind turbine has a drivetrain, and each drivetrain consists of a mechanical part and electrical part with power electronics. And all the wind turbines contribute then to the whole production of the wind farm. This was work we did within the Modelica project. Simpec was a project partner who did very detailed mechanical models, and we contributed the electrical models. So basically, we replaced this up here with that one. Again, if we want to put it to control, we cannot make the most sophisticated model. And in the Power Systems library, we have again a concept to change the granularity of the model. We have phase systems there, so that either for one and the same generic model or for a specialized model, you have to decide which electrical phase system you use. In a very simple case, it's a direct current, here's the connector, sorry. You see this phase system is a replaceable package. I learned this from the fluid modeling, how to do this, how to use this, and introduced it here as well for the electrical systems. We have two vectors, one voltage vector, one flow vector, and each is sized according to the dimension given by the phase system. And we have reference angles, because if you want to apply model components for the voltage and for the currents, then we need additionally information about the angle in the system. And this is communicated with reference angles. And here we borrow, Hans-Jörg did it already, technologies from the multi-body library, that we formulate an over-constrained connector such that in the end of the day, the same phase angle gets communicated to the whole system. And the Modelica tool takes care about over-constrained connectors. It's a problem, of course, if the structure changes. If you break a system, split one electric system in two electric systems, you somehow would need some recompilation of the whole system. So we don't treat this so far. But with the phase systems, we are mostly interested in three-phase. So we can make DC models in three-phase, but all the quantities get scaled to symmetric three-phase systems. We can use DQ coordinates, that we say we neglect transients in the system, but we want to have we want to model active and reactive power. And we also can go up to DQ0 systems, where we also consider transients, electric transients, and non-balanced systems. And this can again be done with a change in the configuration of the model, without having to change the complete model library, and without having first to generate a complex model and then do some simplifications. That's why I'd like to call this constructive model reduction. So we reduce the model with appropriate assumptions during the building process. Let me come to an application example. This is a new interconnector which is currently being built between Denmark, Zealand, and northern Germany. Those are the Baltic 1, Baltic 2 wind farms, which do already exist. There, Denmark plans to build two new wind farms, the Kriegers Flak wind farms. And the idea was, if Denmark makes a radial connection to Denmark and Germany has a radial connection to Germany, why not make a shortcut here, bring them together, and then being able to transfer power. And this is the first time in the world that someone combines wind power collector grids with an interconnector, which poses some challenging tasks on the management and the control of the system. And this is why a so-called master controller was brought in, and we implemented the master controller with the Modelica model and run nonlinear optimization for the prediction of the capacity of the interconnector. So we get wind forecasts, and based on the wind forecast, we must say what is the maximum capacity towards Denmark and towards Germany. This information goes to the electricity, to the power market, and based on this, we get then set points back for the interconnector. And then we implement a real-time optimization, which has to implement those set points by adjusting power reference at the back-to-back. And the actuator is onshore, but the controlled variable is offshore, somewhere in the middle of the Baltic Sea. And this makes the control task challenging, and this is why we have a model-based master controller in here. There may be contingencies. Cables may go out of operation. This reduces the capacity of the interconnector. And then the master controller must react by adjusting the set point, always considering the traded power here. We may also go and reduce the power of the wind farms if it's not sufficient to just adjust the interconnector here. So, by the way, I didn't mention, for anyone who doesn't know the electric system here, this is Sealand. This means this is the Scandinavian transmission grid, or the Nordic transmission grid, and this is, of course, the European grid. So here, this is an HVDC interconnector. So up to here, we have the Nordic grid, and down here, we have the European grid, and this is an HVDC converter. And last but not least, as this is an AC system, we have long cables, we have to deal with reactive power. And this, again, we can do by setting a voltage reference at the HVDC interconnector, manipulating the allowed, or by manipulating the reactive power flow in the middle of the Baltic Sea. We may also set voltage references for the Baltic wind farms as a second resort. And then such an interconnector always also has has a role to save the grid in case of emergencies. And for this emergency power control, the problem is that we have, depending on the wind in feed, we have a time varying maximum capacity towards Denmark and towards Germany. So in this emergency case, we have to calculate limits so that the back-to-back knows how much power it's allowed to push into the system or to draw out of the system, so that the system is not lost as well in the end. So this is the last function. And all those functions are implemented with a model of the interconnector and the model-based control. Here's a screenshot. In this case, we use Open Modelica for the modeling. So you see, it's basically the Power Systems library plus some specific components. And the whole model has a size of roughly 5,000 variables. If you reduce the trivial variables, like stemming from connections, we have 788 non-trivial variables. And this, if we generate the code, we get an equation system of size 81 variables, which has to be solved in a system. And we have 144 measurements, inputs to the system, and 335 model outputs for all the currents, voltages, powers, reactive powers, switch positions in the system. And this is the model that either we run in a real-time optimization or in a predictive optimization over many time steps. I'd like to motivate how we implement the optimization here for this model to achieve the real-time control of this power system. The back-to-back has a capacity of 400 megawatt plus minus, and the installed wind power in the Baltic Sea is about 1 gigawatt, so it's quite important to have a reliable system operation there. If we formulate the optimization problem, then we have in each time step, we have, over all time steps, we have the objective function, the state equations here, the Jacobian of the state equation. We use a multiple shooting, meaning we have explicit state equations that the final state of one time period correspond to the initial state of the second one with a linear constraint. And here we have the constraints which come from the outputs and limits on voltage, bus voltages, currents, and power flows that we have. Here's a screenshot. It's not from this application, but from a similar water network application. Here you see the Jacobian matrix, where we have the state equation here, and we have the constraint equations there in the Jacobian. And each of these blocks, of course, and this is a sparsity that we exploit during the optimization, of course, we have always been exploiting. But each of this block has also an intrinsic sparsity, which is determined by the network structure. What we did within the PARADOM project, that we do also exploit this intrinsic sparsity, that we propagate it through the FMU to the optimization solver. We did this together with discrete time state equations, which are propagated in the FMU to the optimization solver, so that the Modelica tool generates the whole sparsity pattern for us, including also the state equations. And then, as we apply multiple shooting, there is a nice way to calculate this in parallel. We have the multiple time steps for all the blocks that I showed you before. I said that the model has 80 variables in an equation system. And if we are asked to solve this model over a time period, then we can do this in parallel. And at the end, we have to solve an equation system, a large linear equation system, where we can again employ parallel equation system solvers. And we iterate between the equation system solution and the simulation of the model with parallel computers. For the study here, we did follow the old school. We went to a university which has money for computers. And the University of Dresden supplied high-performance computers with unlimited number of CPU cores. And then we concluded that for the industrial project, we bought a computer with 20 CPUs. But I must say, for newer projects, we are really starting already that if we have to do a demanding calculation, we just check the credit card and rent this computer in the cloud. And what you see here, that the 175, this was basically what we had achieved before PARADOM, that if you do a one-day prediction for a system, we needed roughly 3 minutes. But we weren't not only asked to do a one-day, but to do a 3 to 5 day prediction, and the time limit is 5 minutes for the energy market. So this would have been too slow. By using sparse models, we could halve the CPU time, this block sparsity. If we went over from numerical differentiation to automatic differentiation, it became slower again. But then, as we have this big equation system, if we reuse the factors during the computation of multiple Jacobian columns, we finally could get an improvement with the automatic differentiation here. So, and then we applied more and more CPUs. And what's also interesting here is that even the stupid calculation, if we have brute force, then we can get quite good results. But this is quite costly to have such a computer. If we are smarter in the numerics, if we exploit the sparsity, if we exploit reuse of factors in the equation system solution, we can get with less CPUs, like with 5 CPUs, we can get quite reasonable results. So overall, we could reduce the computation time by a factor of 7.5. And as said, this was crucial because the limit given to us by the power market was 5 minutes for a calculation we couldn't do before the PARADOM project in 5 minutes. How much time do I have left? Okay. So I will skip the criticism about Modelica. Virtual power plants. So we started with traditional conventional power plants, saw that the focus goes more and more to electrical systems. We have very demanding power transmission tasks nowadays, particularly if we put offshore wind farms where no people are living. And then what happens otherwise with the big power plants? Here's a nice illustration from Denmark again. This was conventionally, they had a couple of large power plants. Now they have lots of small power plants, which are local CHP plants and wind turbines all over the country. And those should somehow be managed. And what a method to manage that many small power plants to keep this manageable. As you know, power must be produced at the moment when it is consumed. there is a technology called virtual power plants. You treat many small power plants like one big power plant. There, we have a huge challenge in the communication because we need to communicate with all the distributed plants. Again, I think the digitalization helps us a lot because we get the infrastructure. We can say, if you have internet, we can communicate with you through the cloud. And we have GSM and upcoming 5G, so we really benefit from this development here on this side. We connect to the transmission system operators, to distribution system operators, and to the energy market. And in between, we have our model-based optimization. Yeah, why not? I try to show you one example of one of our customers. They are really fast growing. So we started 2012. And the good thing is they didn't ask us 2012 to deliver a system for 8,000 plants. At this time, it was 500 plants. And a year later, they had achieved 500, and then it went on. Now that they have geographically redundant 11 high-performance servers in computing centers and running and optimizing and managing 8,000 small plants with a total power of 7 gigawatt. So to put this in relation, the average power flow in Germany is 70 gigawatt. So this is 10% of the average power flow of Germany. What we provide is telecontrol, the telecommunication, optimization, mostly real-time optimization for the plants, and information management, so store data, make data available for the management of the plants. Towards Modelica, there's a challenge if you make models larger and larger, and if a translator always unrolls the model, you very fast get into limits. So like for 60,000 small plants, this is an example from the last Modelica conference, you have 3 minutes, or between half and 2.5 minutes. If you add 1 decade, you end up in half an hour or several hours translation time. If you keep the arrays during the model translation, the model doesn't really change. There's just some parameters saying, now I don't have 60,000, I have 600,000. Then it's obvious that the translation time must not increase. So we did implementation in Open Modelica, where for this example, we can have a constant translation time of 3 seconds, no matter how large the model dimensions are. The translation time increases a bit if we export an FMU, because there we still have to generate the XML file and have to unroll all the variables. But otherwise, this helped us a lot in current projects where we really ran into all limitations that we could afford with CPUs, memories, and time we wanted to wait for the Modelica translator. So the bad experience. I showed you for the exploitation of the sparsity, finally, we go over to discrete time models where we have synchronous features in Modelica. We have a very nice way to treat discrete time models in Modelica since 2012. But it was not included into the FMI. The proposal was basically ready in 2011 by those 5 authors. It was considered to blow up the FMI 2.0 release in 2014, so it was set aside at that time. Then, as we had this need, I started to work with this. I combined the proposal, simplified it, and then 2017 we had a new proposal. We had also a paper at the Modelica conference in Prague. We had 2 test implementations up and running in Daimler and Open Modelica. But then at the FMI meeting, it was said, hey, you need to join an FMI working group first. We said, yes, of course. We do join the FMI working group. So you see the author list had increased already. We joined the working group. After 1 year, we had done mostly with DSpace and EDF. They contributed their knowledge, and we combined the model exchange with the co-simulation. But then when we expected it would be released in 2018, suddenly FMI 2.1 was canceled, and it's still not released. And if you look at this, I mean, I draw, if young people sometimes, if they want to address something very old, they say iPhone 4S. And this is when we were ready with this. And look what others did during this time. They are releasing now the iPhone 11. And we didn't release anything. Yeah, this is something we have to overcome. Okay. Yeah, another thing is here I opened a ticket about the tables, where we have lots of link dependencies in MSL, basically because there's one C file which refers to any algorithm for HDF5, for compression. And if you want to have a simple table in Modelica and you want to have all the features, then you have those link dependencies. And this is disturbing if you want to go to small embedded devices, if you have all those link dependencies or you need a special tool of the Modelica tool. I might have not been that diplomatic. You can read yourself what I wrote there. But the response was interesting. So within minutes, if not seconds, the ticket was classified as invalid, as will never be done, and it was closed. I reopened it again. Another administrator closed it again, said just a tool issue. So and I asked, yeah, and the solution is, and it's not solved until today. So yeah, accept feedback and be open for further developments if Modelica should have a future. Coming to conclusions, I'd say Modelica served very well for the modeling of thermal and electrical systems over 20 years. This is my time horizon in the Modelica world, so I started 5 years late. Modelica grew with the applications. So it's like for the thermal, we introduced the stream connectors and then the Modelica fluid library. For the digital world, we have been introducing years ago the synchronous models. And at least in ABB, we are using them a lot in the FMUs that we generate. And we have 2 tools that support it. FMI provides mature numerical interfaces, and this FMI 2.0 in particular quite well suited for optimization. In order to get forward, we always needed research projects. So it started with the RealSim, the Eurosyslib, the Modelica, and the PARADOM. In each of those projects, we could make huge steps forward. And yeah, in my impression, the pace of development slowed down dramatically. Like FMI 2.0 was alive 5 years ago, and only small patches since then. And MSL 3.2 was released 9 years ago, and again, only patch versions since then. So that's really my message. If Modelica shouldn't be at the end, we need to do something.
Okay, thank you very much.